There we go. That'll help.
There we go.
Now, the reason this is important is organic chemistry. Everyone says it's the chemistry of carbon. Okay, well then why would I use carbon dioxide as one of my examples when we're looking at, say, orbital symmetries? Well, because organic chemistry is the chemistry of the carbon-hydrogen bonds. So you can still use carbon in inorganic chemistry, but you're not going to see many of those carbon-hydrogen bonds. For example, anyone who goes into biology or medicine, everyone knows the heme ring, the hemoglobin.
Yeah.
Okay, well, you're going to start to learn as you go along. Did you take organic?
I'm in it right now.
Have you heard the term porphyrin ring?
No.
Okay, so in hemoglobin, that heme ring, that is a porphyrin ring. Okay. And so, of course, at the center of the heme ring is your iron atom, and it picks up the oxygen and shuttles that around your body for all your various chemical processes. Well, it can't do that, unless it's able. The transition metals undergo what's called d orbital shifting, based off the coordination chemistry. So, like, you look at this iron, and you're going to learn things like that. What would you say the valency of that iron is?
The valency?
Valency. This is a new idea for you.
I don't know.
That is a 6-valent iron.
Because it has 6 bonds?
Mm-hmm.
Okay.
So you're going to learn the difference between, like, we talked about valence electrons in general chemistry. But when you're reading an article or something and it talks about the valency, this is what it's usually talking about, is the bonding to the individual atom, especially the transition metals. So that is a 6-valent iron. As of this right here, as it releases the oxygen, it'll become a 5-valent. Now, you'll find out in coordination chemistry that every time, constantly, the transition metals are shifting their orbitals up and down in energy. And this is why, for example, these transition metals can be more stable when violating Hund's rule.
That's the spins?
Yeah. So Hund's rule, remember you had to put like an up spin in each orbital before you started pairing? Yeah, well, once these orbitals start changing in their energy, you have lower energy d orbitals and higher energy d orbitals. The lower energy d orbitals will fill before you start putting electrons in the higher ones.
I see.
Also, I mean, you look at people who do what's called cosmic chemistry. So you have people who take all these readings from exoplanets. And so Venus isn't really an exoplanet because it's part of our solar system. You find out, oh my goodness, we found phosphine in the atmosphere. Okay, well, phosphine is a sign of microbes. It can happen. Phosphine can show up under a few different situations, but it is also a good predictor of microbes in an oxygen-poor environment. So, you find inorganic chemistry. I'm not using that, I'm using this. So again, we talked about carbon dioxide. And this is your real difference between your inorganic and your organic. Inorganic will deal with carbon, but organic is the chemistry of the carbon-hydrogen bond. So, and that's really going to be the disconnect. And especially we start getting into things in inorganic, like I talked about, understanding the metals better, which the metals are, once you start going deep into them, they're bizarre. Their behavior is all over the place. You got a very slight hint of that in general chemistry when we talked about variable charge ions. Well, the metals, they really have their own way of behaving. Okay, so we'll just start with something kind of simple, something you've seen before, but we want to make sure we remember: atomic number, mass number, and isotope. So do you remember this formulation, the isotope symbol?
Yeah, I remember that.
Okay, so of course down there you see the deuterium isotope of hydrogen. You have the generalized structure up above. The E is going to be your elemental symbol. Your A, A is your mass number, and based off that little equation there, A is what? What is a P
element
plus?
Number?
No, it's the mass number.
It's like the number of protons. Right? And
what is an N0? This is common notation.
Oh, yeah. Wait, for A? For the mass number?
Yep.
Sorry, I was talking about Z.
Oh, yeah. So your mass number, and again, I'm going to be using all this symbol, like the symbols and language that you're going to see at the top levels. So when you start seeing them in articles and whatnot, I go, oh, I know what that is.
Okay.
But yeah, your mass number is the number of protons plus neutrons in the nucleus. And so, of course, you remember it's the number of neutrons that make the isotope. So, of course, so you see the deuterium isotope of hydrogen, mass number of 2, atomic number, which is one you were thinking of, Z, your atomic number of 1.
Mm.
Your atomic number tells you how much of what is in the nucleus. Protons. All your elements differ by their number of protons. So, of course, there, if you have a 2, that means you have 1 proton and 1 neutron.
Right.
So, relatively simple. But we do need to understand, like if we're in a laboratory and we're examining a sample, so like take metal ores. Well, metal ores, they look like rocks. They don't come out of the ground as like these shiny metal bricks. They don't, they just look like rocks and the metal is in there.
Sure.
And so you got to start figuring out like, well, what's the relative atomic, what you can either figure out relative atomic mass, which is what you see on the periodic table. Remember those, the numbers at the bottom,
yeah.
It's some decimal.
So
that's your relative atomic mass. And then you can start to figure out, you could even start to use it to figure out, what kind of isotopes do I have present? What is their abundance? And so you can do this forwards and backwards. And so you have a generalized equation here where you have the sum of X% of a certain isotope divided by 100 multiplied by its mass plus X% of another isotope divided by 100 times its mass, so on and so forth. And so here, if you're looking at naturally occurring magnesium, let's say you bring up some magnesium and you're trying to figure out, what's the abundance of one isotope over another, which, by the way, this is one of the ways that they do carbon dating.
That makes sense.
It's also one of the ways that we do. So whenever you have someone that tries to argue with you, like the Earth is only 6,000 years old. Mm-hmm. It's like, well, have you ever followed the uranium decay chain? Okay, well, you'd have to do nuclear physics first to understand the differential equations that govern the decay chain. They are extremely exact. And then, of course, you can start doing these relative atomic masses, and you can figure out how much of a certain uranium isotope is left. Mm-hmm. And that tells you that this has to be a certain
age.
Yeah. Your radiocarbon dating could have an error on each side of, I don't know, maybe 1,000 years, plus or minus 1,000 years. To some people, that sounds like a lot. But in terms of 6 billion years, that's like 0.00001%.
Yeah, that's
not that much. But so look here. Let's see if you can calculate the relative atomic mass of these 3 naturally occurring magnesium isotopes. And you remember how to name them, right? You have magnesium 24, magnesium 25, magnesium 26.
Sure.
So when you see an element name with the dash and a number, or an element name and a number, that's an isotope name.
Right. And if it's like iron 3 or something, it'll be in the little.
Now, see, in that there, that right there would be a charge, so an ion. So you're going to have to see some kind of 3+.
Okay.
So it has to be relegated as a charge.
I see.
In this case, where you just have your standard numbers, and especially where they're at, if you see that number in the upper left, or you see the magnesium and then 25, well, your magnesium isn't going to take a charge at plus 25, so that's probably an isotope.
Yeah.
So can you calculate this?
Yeah, like get my calculator, like 78.99 over 100 times 23.9.
Yeah.
Then just add them all.
And you remember what U represents? Now, of course, those numbers are in grams per mole or U.
Is that like AMU? Like
atomic mass units.
Okay. 78.99. Oh my gosh, my calculator, please.
So let's see. You're going to do your magnesium 24, which is going to be your 78.99 over 100 times its mass. Then we need the Magnesium 25. Times its mass. And then the magnesium 26.
So 24.31.
Yep. And then when you look, that's what you'll see on the periodic table beneath magnesium. So again, every element on the periodic table is the relative mass based off naturally occurring isotopes. Okay. Early quantum mechanics. So a bunch of these you remember so you have your Greek letters again. Your energy, its Planck's equation is h nu. H, remember, is your Planck's constant. Okay. You're going to be dealing with a new Planck's constant. Have you ever opened up a physics book and you've seen h bar?
Yeah, that's like something over 2 pi.
Yeah. So h bar, Planck's constant, over 2 pi. So you're going to be seeing that. Not a difficult transition, but it's just one of those where you start seeing these factors of pi popping up all over the place in your calculations. So they're like, well, let's just put that into a new constant. We can just deal with that new constant. So of course, c is your speed of light. That's lambda times nu, wavelength times frequency. Your nu is your frequency. And so then your delta E can become hc over lambda. And a lot of this started with what's called black bodies, black body radiation. So black bodies are like your perfectly absorbing material. They absorb everything. And then they release that energy in the form of heat. And so what this early quantum mechanics ended up leading to is you're able to start then identifying different elements based off their spectra. So here, for example, you see the spectrum of hydrogen. So you hit hydrogen, you excite its electron, and you get these characteristic spectral lines.
Yeah, like you can look through the little thing.
Yeah, and when you do it in a real lab, you have much more advanced equipment. But you get much better spectra. So like when you go to graduate school, you'll have a machine that can generate these.
You just have the little pizza slice thing.
Yeah, but you're gonna have, I mean, you're gonna have to start learning how to understand these spectra. Like what is that? You're gonna get lines. What is that characteristic of? I mean, like in organic chemistry, you're gonna learn to read NMRs.
Right.
But it's like you can't just say, well, I'm going to read an NMR. What do you mean?
To compare it.
Well, it's like, is it a nitrogen NMR? Is it a carbon NMR? Is it a proton NMR? There's like all these different tests, and you're going to have to know the differences between them. But for example, let's say you're looking at the gas argon. Okay, well, its spectrum looks quite a bit different. And these are characteristics. So all of these, so each element is going to have a unique spectrum. Another concept that I want you to start to get used to, see if I can find a place to write this. Well, I'll put it down here. That nu with a bar over the top of it, that's not frequency anymore. This is a factor called wave numbers. Okay. And so a lot of these you're going to start to get in wave numbers. You just need to understand how to change it, which is where this Rydberg equation comes in. Your wave numbers is 1 over the wavelength of your photon. Okay. It's yeah, so it's going to have units, what, inverse nanometers, something like that. Usually it's in inverse centimeters, to tell you the truth. But just start to get to the used to this new notation of the nu with the bar over it. That's going to be wave numbers. Then, of course, you kind of remember the Rydberg equation here. That is where they really started to examine these spectra. And so for hydrogen, for example, you see you have the Lyman series, the Balmer series, the Paskin series, and the Brackett series. Now, only one of those, for example, is visible. Let me see if I think I wrote it down. Okay. I think it's the Balmer series that's visible. The others are going to be like infrared or X-ray, stuff like that. You can still measure them and they're useful for identification, but you can only, so what you saw up here, this is that visible series.
Right, so this is like, energy was put into it and it was excited, and this is it falling back down.
Yep, so energy goes in. And electrons will then jump up to a new energy level. So of course, do you remember what that's called? And you can see it in the spectra. Do you see how there are specific lines?
Yeah, like it's quantized.
Quantized.
Yeah.
There's only certain allowed energy levels, and that's why for each element, these spectra are specific to the element, because each element only has very specific energy levels allowed. Let's see. So yeah, the radiation comes in, your electron or electrons jump up to a new energy level, and then when they fall back down, they release these the photons in these colors, at least for the visible. Some housekeeping. Do you remember? So energy is in what unit?
Joules.
Joules. So you'll be looking at that. And frequency is in what unit?
Hertz or inverted seconds.
Yep, hertz. And hertz is the inverted second. So just so you kind of remember these things as you're going along. So here you're seeing some new, some things you probably haven't seen before. So take, for example, so Planck, and then Bohr was one of the hipsters of quantum mechanics. He did it before it was cool. And so here you start to see some formulations from Bohr quantum mechanics. And now your textbook put in here R as the Bohr radius. I wanted to put in that A sub 0, because a lot of the time, if you're reading textbooks or papers, you'll see you'll see numbers with it'll be a number with a factor of A sub 0 on the end of it. Okay, but that A sub 0 is the Bohr radius. And so whenever you're reading that, you see it's this many times the Bohr radius. And so then you see your Bohr radius is going to be your epsilon 0. H is Planck's constant. N, what do you remember? What is N?
The energy level?
It is. And it's one of your quantum numbers. Which one is it? Do you remember? Principal.
The principal?
N is your principal quantum number.
Okay.
Pi, mass of the electron, and then so over E squared. What is E in this case? Do you remember? Well, I put it on there. It's the fundamental charge.
The charge, yeah.
Charge of the electron. Now, the epsilon 0 you might not have seen before, but you're going to see it in here, and you're going to see it in physics. That is the permittivity of a vacuum. So you can kind of think of that as how much electric field is allowed through outer space. Okay, so you have a distance, you have a space open, it's a vacuum. How much electric field is allowed to actually permeate, like flow through or permeate that space? So that's the permittivity of a vacuum. You can think of it as the capacitance of space. But some of these formulations are going to be very important, as you see when we come up. So your mass times velocity times R. So you have your Bohr radius, velocity of your electron, mass of your electron is going to equal your principal and quantum number times h bar. And so you're going to see this especially pop up when we start talking about the centripetal force on an electron in an orbital. Okay, so this is just a short look at some of the like the Rydberg, the Planck, some of the Bohr formulation, and then kind of talking about a real life application through these various spectra. All right, your introduction to wave mechanics. Now these equations look worse than they are. Okay, your first one is, now this looks a little bit different than what you see in the textbook, but you can like just do algebra and go between this Schrodinger equation and the one in the textbook. So the Schrodinger equation is called an eigenvalue equation. Okay, and you see, for example, so psi is going to be your wave function. You're going to start to get used to this idea, and we'll cover it in much more depth in physical chemistry, called the operator. Do you see that h bar squared over 2m and the second derivative with respect to x?
Yeah.
That right there is called the energy operator. So what it does is, you notice it actually performs an operation on the wave function.
Okay.
And what you get out of that then is the energy of the system. So all of these, your angular momentum, your energy, your regular momentum, even your position, like your average, they're all going to have operators. And so you're going to start to get used to this whole idea of operator mathematics. Now, down below, I did go ahead and give you so one of these, that top one is your time independent, because if you just look up the Schrodinger equation, you're also going to see derivatives with respect to time. However, and this is where people's minds start getting blown, in quantum mechanics, space and time are you can separate them. Space and time can either act together, or they can be their own individual realms, and they can be completely separated and act independently. I'll let you contemplate that one for a while. I don't feel like my space should be influenced by time. Oh, okay, well.
Yeah, why not?
But this is your time-independent one-dimensional Schrodinger equation on the top. I did go ahead and give you the formulation of the three-dimensional Schrodinger equation, still time-independent, down at the bottom, because it introduces you to a new operator you've never seen before. Now, up on the top, that derivative looks familiar. You've seen those. What if I told you that that one on the bottom is also a derivative? That is your Laplacian operator.
Okay.
So if you ever hear someone say, take the Laplacian, that's it.
So it's just like a particular way of doing your derivation?
Yep. Well, it's three derivatives in one. So here you see it broken down. Some people call that upside down triangle del. I don't know, depends on who's writing. But what that translates into is these three your partial derivatives in each dimension. And so then you see the Laplacian is just the square derivative, the second derivatives. And that's so it's not the Laplacian squared or the del squared, it's the second derivative.
I see.
And of course, do you remember we talked a little bit about different partial derivatives?
Right.
So real simple. Let's say I did dx, and then I'm going to do 2x squared y to the 4th. Okay. Do you remember what I said the partial does to that?
You're only doing it for x, and you treat y like it's just any number.
Right. So this would become 4x y to the 4th. So the derivative only acts on the x squared. Now, in math class, we skip a lot of things, because in math class, they would tell you have to do the multiplication rule all the way across and find out that the derivative of 2 and the derivative of y becomes 0. In physics, we kind of skip some of those steps.
For sure.
Okay, so what that means is, let's say you're looking at the Laplacian of your wave function. This translates into and so then you would just take psi, whatever function psi is, in there and perform each operation on it and add them all together. Another thing up here, I use the term eigenvalue function, which is what the Schrodinger equation is. Eigenvalue, of course, it's a nice German word. That means when you are performing an operation on this specific equation or this physical system, eigenvalue means it has a characteristic value. So you perform this operator and you get the energy. And you'll see as we go along that these wave functions are going to change based off, like, let's say you're in a 1s orbital, a 2s orbital, a 2p orbital. You're going to see how those change. And you can perform this operation over and over again on each one and get a different characteristic energy. This was the beginning of what they came to understand as quantization. So it wasn't this range of energies, it was eigenvalues, specific energies for specific physical realities. And so that's what eigenvalue means if you start to look at that. But Another way you can identify an eigenvalue is, let's just take this operator. This is called the Hamiltonian, okay? So let's look at, so that's the way you write an operator. You write, so this is like the Hamiltonian, and then the hat on it means operator. So now you're going to start getting used to hats in terms of unit vectors and hats in terms of operators. But we're not going to use a lot of operator notation this semester. We'll do that as we move on. So you will see Schrodinger equations represented like this. Okay, it's the same thing. It's the same thing as above. Okay, and what you notice is as you perform an operation on your function, you get a single characteristic value. This is the way you can, and you get the function back. That's the key. You get psi back with that characteristic energy now being pulled out of it due to the operator. That is an eigenvalue equation. Once you're able, you get a little practice identifying that structure, and you'll be able to see them all over the place. Okay. So to kind of continue here, so what this would end up becoming, I'm really bad at these upside down triangles.
Yeah, me too.
So of course, this would just distribute.
I'm bad at the side as well.
Yeah, that's why I just do that little square box thing, because they want you to draw it like this with that curve, but I can never do it right. In grad school, I had a lot of my professors did this,
Yeah.
and they just didn't try to do the swoop on the other side. And there were times it was all cockeyed, and I was like, is that an X or what?
Yeah, what's going on?
So that's a short look at going a little bit beyond the book. You see your Laplacian. Again, it's something you're going to see in upper level textbooks. And so you just start to, this is more getting used to the language, but you also see here that whatever psi is, that del squared, it's not really anything to be afraid of, because you're going to distribute that function in and take each individual partial derivative. And then you just add them all together. So right now you're doing more algebra than you are calculus.
Okay.
So as you see now, you would do one step of calculus, then you go back to your algebra. That's kind of how quantum mechanics goes. We're not in quantum mechanics. Rarely do we make you reparameterize integrals or change coordinate systems in the middle of it. That's all for the math department. They can do that. Okay, now. Okay, so put H bar in there. I also want you to know Euler's formula. Okay, because now we're going to start, I think this is where, yeah, we're going to start talking about the solution to the Schrodinger equation. Okay, and Euler's formula is going to come into it. A lot of textbooks skip straight to the general solution, but I want to show you how we get there.
Sure.
And Euler's formula is not something that you're going to derive, it's just something you're going to use. So first off, what is the I?
Is it an imaginary number?
Imaginary number, square root of -1. Of course, H bar is your Planck's constant over 2 pi. And the way this is solved, especially for so let's look at hydrogen, single electron. We solve this by using what's called a particle in an infinite square well.
Okay.
So the way we can model this is you can say, well, there's our well. Outside the well, potential is infinite. Can you give me a physical reality that this would represent for an electron?
So like, is this like being outside of the orbitals versus being in them? Or
Which is called, do you remember what that's called in chemistry? Ionization.
Ionization? Okay.
So when an electron does not have enough energy to ionize, it is essentially trapped in an infinite well. And this is what we call bound states. You're going to start to see energies pop out that are negative. It's like, why does it have a negative energy? Okay, well, in chemistry, a negative energy is a bound state. The electron has not escaped its molecule or atom. It's still within the orbitals. It is bound. Okay, now, inside the well, V equals 0. And then, of course, we have X equals 0. Oh, let's see. Since I have an L, I should change it to an A. Because your textbook uses A. But yeah, I'll do. Okay, so we're just going to do this in one dimension. Then you'll start to notice that inside this well,
Is it like a standing wave?
but only these very specific energy levels are allowed. Now, you notice, let's go back up and take a look at this and try to figure out what the Hamiltonian actually has. You notice I have this portion and this portion. Do you remember what V is?
Capital V?
It's not volume, it's not velocity. In physics and in energy, now you're going to see it in physics represented as volts, but then you're going to hear it. So in energy terms, V is going to be, V or U is your potential. So this is a potential energy term. If something plus V gives me my total energy, what do you think the h bar squared over 2m and the second derivative are?
Is that like,
V is potential energy.
so like location or something? Or is
What
it the mechanical?
total energy is potential plus
The mechanical, like the
what part of the mechanical?
the kinetic?
Kinetic.
Okay.
So that first term there, that's your kinetic energy term. Okay. So your Hamiltonian. We'll have a kinetic term plus a potential term. Okay, so okay, and let's talk about what the reality of V is. Because we're going to be dealing again with this in electricity and magnetism. So potential, you have an electron, you have a nucleus. What do you think the potential between those two could be?
The potential?
Now remember, your electron at this point, at V equals 0, is settled into its orbital. It's settled into its quantum level.
Right.
But if you start pulling that electron away, potential increases based off what?
Like, is it the, I don't know,
It's called the electrostatic potential.
electrostatic?
So you have the positive charge of the nucleus, the negative charge of the electron, and these two want to settle at a lowest energy. Okay, that lowest energy is where V will equal 0. But if I start pulling those two apart and I make that electron go to higher and higher energy levels, that potential starts to increase, trying to pull it back down. So this is what we call, so this would be a representation of an electron in its ground state. Okay, V equals 0. Now we can start to actually solve the Schrodinger equation, because you'll notice with V equals 0, we just pull down that equation from above. Schrodinger equation is now shortened to this, because you notice the potential term has disappeared. Okay, well, let's start doing some algebra, because we want to solve this differential equation. So on this side, we're going to get -2 me over h bar squared psi. And what we're going to call this, because this is going to be negative k squared psi. We're going to say that all of this becomes a constant that we're going to call k squared. we call it k-squared because we want to end up making it match the order of the derivative. And that's so it gives us a nice easy function to solve for. So that means that your k value going to be the square root of 2 mass of your particle times its energy over h bar. But now we have a nice easy differential equation that we can solve for. Okay, so let's think about that. We have so now there's a lot we could do. For this one, I'm gonna teach you how to use some logic instead of going through the characteristic equation and taking a lot of extra time. Okay, now what we're looking at here is the second derivative of some kind of function gives a constant plus that function back. Now, I guess you could say that if I had sine of theta, the first derivative is cosine of theta, the second derivative is negative sine of theta, and you remember those just go back and forth. Same with the integrals. You go from like, let's say you take the integral of negative cosine, that becomes negative sine. The integral of that becomes positive cosine. The integral of that becomes positive sine. The integral of that becomes negative cosine. They just keep going in a circle. Now we could go that route, but there's a much easier way to do this. Do you know of any function that gives itself back upon taking the derivative? Any?
Yeah, probably.
So what if I did? Have you done this derivative yet?
E to the x, because it'll just be the thing on the outside multiplied times the e, right?
This one right here is just straight e to the x. So the derivative of your exponential function always gives itself back.
I see.
Okay, so then we say, well, but I have to have a constant come out of that. So, okay, so let's say, and I'm going to come up with a function, then I'm going to test it, okay? So what I'm going to say, I'm going to start with here, e to the kx, okay? Well, that's great. So let's do this. Have you done use substitution yet?
No, but that's the first lesson in Calc 2. I just haven't done it yet.
So here's how we do it. So I'm going to call kx u, okay? And then you do the derivative by the chain rule, okay? So the way this works is I'm going to say, well, what if I just take du ddx? Because again, you always remember you can multiply by 1. Don't say that to your math teacher, they'll flip a lid. Because they're like, derivatives are not fractions. Yeah, well, it works.
Oh.
But what this can become then is that. Do you see how that all works out there? So I've called u kx. So now what I'm going to do is take du dx, multiply it by ddu of e to the u. So since u is kx, what is the first derivative of that with respect to x?
Is u is kx, what's that? So it'll just be e to the kx, or e?
So let's do.
Or is it just k?
Yes, just k. Because the derivative of u with respect to x is the derivative of kx with respect to x. It just puts out k.
Okay.
So what we're going to get is k ddu of eu. We know that that's eu because it just gives the function back. And then I'm going to put k e and just put u back in. Okay. Now, do you remember that a second derivative is just a chain of derivatives?
Yeah.
Okay. So if I want the second derivative of this function, I just now take the derivative of our solution again.
Mm.
Because I've already done the first derivative. Now I just take the second derivative.
Right.
If you had a third derivative, you do first, and then your second, and then your third.
Right.
So now my second derivative is it's going to be this. Because that solution there is the first derivative. Okay, well, once again, and then we're going to have our, let's see, du dx, d du, k e to the u. K is a constant. What do we do with constants and derivatives?
Cancel them out.
We pull them out front.
Oh, we'll pull out front.
Yep, so the k is not even going to get touched here, okay? So we're just, again, so the d to du, the du dx is going to be k. And then I already have a k there. And my d to du of eu gives me back eu. So you see, we've come up with a function here that works pretty darn well. But we don't have the negative sign on that k. Okay, now first off, do you get how we did this chain here?
Yeah, I see what's happening.
Okay, because this will just take some practice.
Yeah.
Now, because we're running out of time, we don't have a negative sign. We fix that, and you'll see later on when we get to the general solution, this is why Euler's formula is important. Well, physicists know we can usually get a negative sign from a second derivative by bringing in I.
Mm.
So what if we changed we want that negative sign. So what if we changed because we know that the kx works. That function will work for the structure of what this equation should come out to be. We want that negative sign. So what if we change psi to the ikx? Okay, we'll pick it up there on Wednesday. And maybe in the meantime, see if you can actually do the first and second derivative of ikx.
Yeah.
And remember that I squared is -1.
Right.
Okay.
All right. I'll try it. And I'll learn about U substitution. I think I definitely did it in Calc 1, but just like probably very basically.
And remember, that's called the chain rule, what we did
Yeah.
there. Okay. Okay, so we'll just continue on from here next time. And we'll just keep plowing ahead.
Sure.
But I did want to ask you a question. So you had talked about like doing this quantum mechanics in this kind of depth.